Everything so far assumed independent draws, or at least draws whose limiting behavior didn't depend on order. Real systems remember, tomorrow's weather depends on today's, not on last month's. A Markov chain builds exactly that in. The next state depends only on the current one. Time to see what that buys us. The Markov property. Given the present state, the future is independent of the past. The probability of the next state depends only on the current state, not the whole history before it. That conditional probability is the transition probability collected into a transition matrix P, whose rows are probability distributions. Each row sums to 1. Take a two-state weather chain, sunny and rainy. Sunny stays sunny 80% of the time, tips to rainy 20%. Rainy clears up to sunny 40%, stays rainy 60%. How likely is it to be sunny 2 days from now, given it's sunny today? By the Chapman-Kolmogorov equation, just multiply. The two-step transition matrix is P squared. In general, the n-step transition matrix is P to the n-th power. Entry I, J, is the probability of landing in state J after n steps, starting from state I. Watch the rows of P to the n as n grows. They start out distinct, but converge, every row approaching the same distribution, regardless of where you started. That common row is the stationary distribution, pi, a row vector satisfying pi times p equals pi. Once you're distributed according to pi, one more step leaves you distributed according to pi. For the weather chain, solving pi p equals pi gives pi equal to 2/3 sunny, 1/3 rainy, in the long run, no matter which day you started counting from. It's the law of large numbers. One level up, the chain forgets its starting point and settles into a long-run distribution. That settling isn't automatic. Two conditions matter: irreducibility, meaning you can eventually reach any state from any other, and aperiodicity, meaning the chain doesn't get trapped in a rigid cycle. Break aperiodicity, and convergence fails. A chain that deterministically alternates between two states never settles. Its distribution keeps oscillating, forever out of step with pi. With both conditions, the stationary distribution is unique, and p to the n's rows converge to it from any starting point. That's the fundamental theorem of Markov chains. A Markov chain, the next state depends only on the current one. Transition matrices encoded. Powers of the matrix give n-step probabilities. And, under irreducibility and aperiodicity, the chain converges to a unique stationary distribution. It's discrete time, discrete space randomness with memory exactly one step long, the simplest stochastic process, and the model underneath everything from pagerank to Markov chain Monte Carlo. Next, Poisson processes, the continuous time cousin, where events arrive randomly in continuous time instead of a state transitioning in discrete steps.